So from the very beginning with the T2C-136, I was trying to minimize the amount of development time and resources in the project. It was, pretty hard to justify the development of this glider from the very beginning because there was the expected sales and markets for this glider was very small. So, I committed one prototype. I made it very close to the companion size, the 144 T2. The initial development went really well and quick, and everything was going smoothly. So the last part of the development process was the vehicle testing. And, the uncertainty in the vehicle testing was probably principally with the longitudinal stability, the pitch testing of the glider, because especially with high-performance gliders, we have very thin margins with that, and it's, we often have to make adjustments to make the glider, pass those parameters. But 136 didn't have a problem with that. Everything went smoothly, so we got to the structural load testing. And that's where we had the surprise. We have a joke, Mike and I have a joke with this vehicle testing when we have a surprise. And this is by no means the first surprise we've had, but again, I wasn't expecting any surprise with this glider. It has the same structural components as the two larger gliders. The 154 in particular is a much bigger glider. It has the same crossbars, the same structural center that supports the two carbon crossbars, and it's a much smaller glider with less area, so we would expect much lower loads. So we were doing this -30 test, this nose down into the wind test, and we had a premature failure. This center structural spar that supports the carbon crossbars, the negative loads, buckled. And as I said, Mike and I have a standing joke about this because years ago, one of our competitors who often had trouble certifying his gliders and had marginal compliance with his structural load testing used to complain that there were mysterious gusts that hit the glider that missed the airspeed indicator that documented the load tests. So whenever we have an unexpected failure like this, we say, well, it must have been a gust that missed the airspeed indicator. So, which obviously it isn't. This is ridiculous. The glider failed. But again, this -30 test is very sensitive to the orientation on the vehicle, and crosswinds can cause the glider to skew sideways and load the glider in a configuration that puts unreasonable loads on the structure. So it really, I thought it was most likely that the glider had become unstable and had yawed on the test vehicle and had been subject to unexpected loads. So put it back together and went out and tested it again. And it broke at exactly the same speed again. And so now there's two failures. So I thought, well, okay, no gusts that missed the airspeed indicator. Obviously this is a problem, but why is there a problem? So the geometry of the glider is very sensitive, and the loads on the structural member that failed is very sensitive to the sweep in the crossbar, which is associated with the loose VG setting on the glider. That is the configuration of the glider where it's most maneuverable and easier to control. So, and I'm aware of this, and this was part of the preliminary design. I want to maximize the VG range, and on the forward end, I'm limited by the structural constraints of the crossbar and the crossbar beam. And on the back end, the crossbar hits some other structure in the glider and can't be pulled any further back. So I want to have this wide VG range. Now we've gone through all the flight development on the glider, got it exactly where we want, got this failure, and I can solve the problem by just restricting the VG range to 1 inch tighter. In other words, giving away a little bit of my loose VG range. But we didn't really want to do this because, again, I designed this glider bigger than I wanted to initially to make sure that it, have a higher likelihood of success without subsequent prototypes, and to make it, more likely to fly properly with, minimizing the development time. So now, because it's a bigger glider than really is optimum for these lightweight pilots, I especially don't want to give away any of this loose VG range and give up any controllability. So I have to start figuring out, well, why is this failing? Because it shouldn't be failing. Well, it turns out this beam is it's pretty easy to manage this, to analyze the stresses on this beam member. I have analytical tools, finite element analysis and stuff, but you can do hand calcs and figure it out. And it still was kind of a mystery. It seemed like it should have enough margin to pass. Well, it turns out that it was a buckling problem, and buckling failures are a little bit different than tensile failure in a structure. And anyway, it's one of those things that, in hindsight, it's really clear, like all of these things are. When you have a failure and it's unexpected, sometimes you don't anticipate it, and there's no way you really can anticipate what these things are. But, after you find out what the cause is, the root cause is, you say, of course, why didn't I think of that? So that required redesigning this center structural part, and it required a minimal change to this part. Basically, it's kind of an I-beam type structure, and I just thickened the flange a little bit, and some other minor changes that made it 30% stronger in buckling, and retested, and it was fine.